Hey everybody. Today we're talking about the central limit theorem, which describes the sampling distribution of the sample mean x bar. You need to make sure you're fairly comfortable with the idea of the sampling distribution of the sample mean before this video will really make any sense. I have a whole lecture on that. I'll throw a link to that up top. So here's what the CLT says. Suppose you have random samples of size n drawn from a population with mean mu and standard deviation sigma. If n is large, and 30 is pretty much always sufficient, then the sampling distribution of the sample mean is approximately normal. If the population that you're sampling from is actually normal, then the sampling distribution of x bar is exactly normal, regardless of the sample size n. Moreover, it's always the case that the expected value of x bar is the same as the population mean, and the standard deviation of x bar is equal to the population standard deviation divided by the square root of n, the square root of the sample size. For instance, suppose we have a call center where the lengths of calls have a mean length of 2 minutes and a standard deviation of 3 minutes, and we want to know the probability that 40 randomly selected calls have mean length than 2.5 minutes. This is actually a pretty realistic question if you imagine yourself as a manager of this call center trying to plan your staffing needs for known call volume. Notice that we don't know much about the distribution of call lengths here. We know the mean and the standard deviation, but we don't know anything about the shape. In particular, it's probably not going to have a bell shape. You can't have calls of negative length. So I'm imagining that probably we have a distribution with a pretty strong right skew. It's going to be a lot less likely that you have very, very long calls than pretty short ones. By the central limit theorem, the sample mean x bar has an approximately normal distribution with mean of 2 and standard deviation 3 divided by the square root of 40. So the mean is the same as the population mean. The standard deviation is the population standard deviation divided by the square root of the sample size. The variance is going to be the square of that. We can summarize by saying that the distribution of x bar is n of 2, 9 over 40. So that n notation wants mean and variance, not mean and standard deviation. So we need to compute the probability of getting a random value less than 2.5 in this distribution. Calculation's best done using technology. I use R, and so we're using the CDF of that normal distribution. In R, that's p norm. We feed it the value that we're interested in, 2.5, then the mean, 2, then the standard deviation, 3 divided by the square root of 40. We get about 85.4%. So the chance that 40 calls to the center will average less than 2.5 minutes is just a little more than 85%, approximately. Let's do another example. Let's get into this in a little bit more depth. A random number generator produces random integers from 1 to 10 with equal probabilities. So it's an extremely simple probability histogram. Now let's imagine using this random number generator twice and taking the sample mean. The result is again going to be between 1 and 10, but now the results are not going to be equally likely. We're a lot more likely to have results near 5.5 and a lot less likely to have results near 1 or 10. So I did 1,000 trials like this. So in each trial, I got 2 random values and took their average. So when I have 1,000 trials of samples of size 2 with their averages, I get a histogram that looks like this. Now, this is through a random process. If you were to do 1,000 trials on your own, you'll get a slightly different looking histogram. Similarly, I can do 1,000 trials with samples of size 10. The histogram is now beginning to have a slightly bell shape. You can already see this. Obviously, there's one bar that's kind of out of line just through some random chance. Notice that the results now are all pretty well crammed in between 4 and 7, although there are a few more further away. We don't have any results that are really near 1 or really near 10. Continuing on, here's 1,000 trials with samples of size 100. And the bell shape is very, very clear already, even though it's not perfect. Also notice that most of the data is now crammed between 5 and 6. So the spread is very much going down as the sample size gets larger. Finally, here's 1,000 trials with samples of size 1,000. And a normal curve is going to fit these results exceptionally well. Also notice that the spread has continued to drop. Let's look at this a bit more mathematically. If we randomly select a single number between 1 and 10, obviously each value has probability 1 in 10, and we can compute the mean and standard deviation of that discrete probability distribution very directly. And I recommend you try that for practice and confirm that you get a mean of 5.5 and a standard deviation of 2.87. Now, if we take samples of size n, the sample mean x bar is going to have a distribution that's approximately normal, with a mean that's exactly the same as the mean that we already computed for individual draws, 5.5, and a standard deviation that's scaled down by a factor of 1 over the square root of the sample size. So the standard deviation of x bar is sigma over the square root of n, 2.87 divided by the square root of n. Now, that is not the standard deviation for a single draw of size n. Rather, we're imagining all draws of the same size. What's the standard deviation going to be for that sampling distribution? For instance, consider samples of size 10. We had 1,000 randomly generated sample means, and the average of those 1,000 randomly generated values was 5.5312. The standard deviation of those 1,000 randomly generated values was 0.9043. Again, since that's 1,000 randomly generated values, if you do this on your own, you won't get exactly those same numbers. The theoretically predicted values are mu of 5.5 and sigma of 0.9083. So the randomly generated values were pretty close to the theoretically predicted ones. The central limit theorem says that the sampling distribution of x bar is approximately normal for large n, and suggests that n equals 30 and certainly counts as large. But in fact, n equals 30 is usually very conservative. If the distribution that you're sampling from isn't highly skewed and doesn't have extreme outliers, a much smaller n is almost always acceptable. In our example, we took random samples of numbers between 1 and 10, all with equal probabilities. And the bell shape was very clear even for n equals 10. So obviously here we're sampling from a distribution that isn't highly skewed and doesn't have outliers. But if that were the case, a larger sample size like 30 would be necessary.